Hey everyone, welcome back to the Physics Vault. If you love physics that blows your mind but still feels easy to follow, you're in the right place. Today we're exploring one of the coolest ideas ever, the idea that everything in the universe, every particle, every force, you, me, stars, everything is made of tiny vibrating strings. And excited, not point-like dots like we used to think, but super small, one-dimensional strings that wiggle in different ways. These vibrations don't just create matter, they also bring gravity into the quantum world. This is string theory, the dream of uniting the tiny rules of quantum mechanics with Einstein's huge-scale relativity. Ready to unlock this secret? Let's dive in. If you're new here, smash that subscribe button and hit the bell so you never miss a deep dive like this. Let's go. You know how physics has two superstar theories? Quantum mechanics rules the super small world. Electrons, quarks, photons, everything probabilistic and double-layered. General relativity, Einstein's baby, rules the big stuff. Gravity bending space and time around stars and galaxies. Both work amazingly well, until you try to put them together at the tiniest scales. At the Planck length, that's about 10 to H or 35 orb meters, smaller than anything we can imagine. Gravity gets quantum too, but when you plug point particles into the equations, you get infinite numbers that break everything. Chuckles. It's like trying to mix oil and water, or worse, like your phone's calculator crashing when you divide by 0. Scientists spent decades hunting for a fix. String theory is the leading candidate that actually works. Instead of zero-dimensional points that can crash into each other infinitely, everything is made of tiny strings about the Planck length long. They have size, so no infinities. And here's the magic. One special vibration of a closed string loop is thus Graviton, the quantum particle of gravity itself. Gravity isn't added by hand. It pops out naturally. That's how we finally unite quantum mechanics and relativity. Imagine a guitar string, pluck it gently, low note, pluck harder or at different spots, higher harmonics. Each vibration pattern is unique. In string theory, the fundamental strings do exactly that. There are two types. Open strings, they have two ends. These usually make the particles we see in the standard model. Electrons, quarks, photons. Closed strings dash are perfect loops with no ends. These travel freely through space, and as I mentioned, one mode is the graviton. The strings are so tiny that from our scale they look like points. But their different notes or vibration modes give every particle its mass, charge, and spin. A low vibration might be a massless photon. A higher one could be a heavy quark. It's like the universe is a giant cosmic orchestra, and every particle is just a different musical note played by these strings. They don't sit still. They move, split, join, and interact by touching at ends or crossing paths. All of physics emerges from how these strings dance. Here's where it gets wild. For the math to work without weird, faster-than-light particles or other glitches, the strings need more than our usual 3 space plus 1 time dimensions. Bosonic strings want 26 dimensions total, superstrings need 10, and we'll get to M-Theory's 11 soon. But we only experience 4. Why? The extra ones are to compactified. Curled up so small we can't see or move in them, just like a garden hose looks like a 1D line from far away, but up close has a circular dimension around its width. Those extra 6 dimensions in superstring theory wrap into special shapes called Calabi-Yau manifolds. These tiny geometric sculptures actually decide what particles and forces we get. Change the shape slightly, and you might get a different universe with different physics. It's mind-blowing. The properties of our world are coded in how these invisible extra dimensions are folded. Early string theory, bosonic only had force-carrying particles, bosons, but we need matter particles, fermions too, electrons, quarks, so we add supersymmetry. A beautiful symmetry that pairs every boson with a fermion partner. This cancels out dangerous quantum effects and makes the theory stable. That gives us 5 consistent superstring theories in 10 dimensions. Type 1, mix of open and closed. Types Tessier and type B, closed strings, slightly different symmetries. 2 heterotic versions, closed strings with special mathematical groups for forces. They all look different at first, until we discovered dualities. These are mathematical transformations showing they're actually the same theory seen from different angles. Like flipping a coin, heads or tails, same coin. One duality swaps strong and weak forces, another swaps how strings wind around extra dimensions versus moving through them. In 1995, Edward Witten dropped a bombshell. All 5 superstring theories are just different limits of one deeper theory. M-Theory. Living in 11 dimensions. The M could stand for membrane, mystery, or magic. We still don't know the full equations. M-theory includes not just strings, but higher dimensional objects called branes, like 2D membranes or 5D, 5 branes. Our strings can even be the edges of these branes or stuck to them. Everything, forces, matter, gravity, emerges from how these branes and strings move and vibrate in this 11D world. M-theory finally ties the whole family together into one elegant framework. String theory isn't just beautiful math, it solved real puzzles. Take black holes. Quantum mechanics said information gets destroyed inside them, but that violates rules. Using D-branes, physicists counted the exact number of string vibration states on the black hole surface, and got the exact entropy Stephen Hawking predicted. Information is preserved after all. Then there's the ADA-SC-CFT correspondence, one of the most powerful ideas ever. It says a string theory universe in a curved space is exactly equivalent to a quantum field theory on its flat boundary. Like a hologram, the 3D movie is fully encoded on a 2D film. This holographic principle helps us understand black holes, quark-gluon plasma from particle colliders, and even some materials here on Earth. String theory is already giving us tools to solve problems in other areas of physics. So where are we today? String theory beautifully unites quantum mechanics and relativity. It predicts the graviton, explains forces, and handles black holes. But we haven't found direct proof yet. The Planck scale is way too tiny for our accelerators. There's also the landscape problem. The extra dimensions can fold in about 10,500 different ways, each giving a different universe. Which one is ours? Some scientists use the anthropic principle. We live in one that allows life, but others worry it makes predictions too vague. Critics say it's not fully testable yet. Supporters say it's the only consistent quantum gravity we have, and its math keeps producing breakthroughs in pure mathematics too. Future experiments, cosmic rays, gravitational waves, or new colliders might give hints. Or maybe we'll find indirect signs through cosmology. Think about it. The universe isn't cold particles crashing randomly. It's a symphony of vibrating strings playing different notes to create you, me, stars, and the forces that hold reality together. String theory shows that quantum weirdness and cosmic gravity are two sides of the same song. Whether it turns out to be the final answer or leads us to something even deeper, it's pushing human knowledge forward in incredible ways. What do you think? Is the universe really made of tiny vibrating strings? Drop your thoughts in the comments. If this deep dive helped you understand one of physics' biggest ideas, give it a thumbs up and share with your friends. Subscribe for more mind-blowing physics made simple. Thanks for watching the Physics Vault. Stay curious, keep learning, and I'll see you in the next one. Take care.